All right, guys, so just follow along here, okay, as we answer these questions. So, for our first one, list the 3 points of the, or sorry, list the points, the 4 points of the atomic theory. Okay, first point, what's everything made out of? Small particles called atoms. If they have something about all matter being made of atoms, that's good enough for me. Okay? All right. Second point. All atoms of the same element are identical. If they have something about atoms of the same element being identical or atoms of different elements being different or both, good. That's the gist of the second point. And now you know why I usually have everything typed up ahead of time. My handwriting is an atrocity. Okay? It has never been good, and it never will be. Okay? All right, number 3. Instead of me giving it away, let's have someone tell me what it is. Okay? Right, atoms can combine in simple whole number ratios to make compounds. So if they have something about atoms going together to make compounds, and they have something about whole numbers in there, good enough. Okay? Something like that. Okay, and the fourth point is basically what happens in a chemical reaction. Atoms can be separated, joined, or rearranged, but they can't be turned into other things. If they have something along those lines. If they say in there that you can't turn one atom into another, okay, if they have something about, that they separate, join, or rearrange, that's also fine. Basically, they need to tell me what happens in a chemical reaction, because that's what the fourth point, okay, deals with. Okay, reactions of some kind there, some description of that. Okay, give you guys a little leeway on that one. Who came up with those 4 points? Dalton, right. Okay, they don't have to have John Dalton, just Dalton is fine. Okay, 1 mark for that. So, sorry, these were each 1 mark, right? Each point was 1 mark. Okay, Dalton, 1 mark. Name and describe the particles of the atom. Okay, and we said all we want here are the names and charges. Okay, so protons. Okay. Positive. Okay, neutrons. And I never spell neutrons right. I might have actually there. It never looks right, no matter whether I put the U or the E first. Neutrons are neutral. Okay, and electrons, okay, are negative. That's shorthand, by the way. Okay, if you go to university, you won't need shorthand because you'll probably take a computer with you. But in my day, you actually had to keep up with a guy who talked about as fast as I'm talking right now for an hour and a half. You learned to write shorthand real fast. Okay. Number 4. What particle did J.J. Thomson discover? Electrons. Okay, sorry guys. The way the marks go on this one, they have to get both parts right. Okay, if they have protons are positive, 1 mark. Neutrons are neutral, 1 mark. Okay, electrons are negative, 1 mark. There's no half marks there. They either got it right or they didn't. Okay, they either matched them up with the right charge or they didn't. Okay, so 1 mark for electrons. Who proved the existence of the nucleus? Right, Rutherford. So 1 mark for Rutherford. Okay, and draw a picture of de Broglie's model of the atom. Okay, so de Broglie was the electron cloud guy, so we could say, okay, there's a nucleus, and then I can't draw either. Okay, so if they have something that looks like a nucleus and a cloud around it, good. Okay, they knew it was the electron cloud. They probably also, just to be sure, wrote electron cloud underneath. Okay, something like that. That would be fine. Okay, as long as they knew de Broglie made up the electron cloud model, they're set. Okay, so that is going to be out of 1, 2, 3, 11. Okay, out of 11. Perfect. So give them a mark out of 11. Okay, hand it back to them. When you've had a look at it, put it in the box up front here, please. All right. So what we want to be able to do here, guys, okay, and this should be, most of this is going to be reviewed. There's a few things we're going to add, okay, about different types of metallic atoms, okay, and how their ionic compounds get named a little different that you might not have learned in grade 9, okay, but most of this should be familiar to you from grade 9, okay. So our key points, okay, we want to be able to identify a compound as ionic or molecular. Anybody remember how you do that? No, you're on the right track. Exactly. Okay, I think what it was Quinn, right? Yeah. Okay. I think what you were saying was it was from both sides of the table, I think was where you were leaning. But yeah, that means that one is a metal, one is a non-metal. In an ionic compound, in a molecular compound, they're both, okay, from the right-hand side of the staircase, okay, they're both non-metals. Okay, those are molecular compounds. All right, and be able to write formulae. That's plural for formula. Okay, formulas is not a word. Okay, and proper names for chemical compounds. Right. So, like I said, this should be a review. It should go pretty fast for us. Okay, so ions and ionic compounds. The thing to know about ionic compounds, like we already said, they occur when a metal and a non-metal react to form a new molecule. So, if you've got your notes package, always a good idea if I enunciate or I actually underline something, okay, yeah, it's probably important, okay? If I slow down and really, kind of make a big point of something, it's probably important. All right, in these molecules, electrons are typically lost by the metal and gained by the non-metal, right? And that's just kind of a general rule. Metals typically are not very electronegative. They tend to lose electrons easily in a reaction, whereas non-metals tend to be more electronegative and they pick them up, right? That's not something that's going to be really important for Science 10, but it kind of explains why these charges move around a little bit. All right? All right, so in a very simple compound like when we have sodium and chlorine go together, okay, sodium usually loses the electron and it goes over here to chlorine, okay, and so if sodium loses an electron, does it now have more protons than it has electrons? Yeah, so it has a charge of +1, okay, because it's down an electron. Now it has one more proton, so it has a charge of +1, okay. Meanwhile, chlorine has picked up that electron, okay, so it now has a charge of -1. Okay, and I think you can see that a little bit better in your notes package than it showed up here, because I just tried to write over green in green, which makes a lot of sense. Okay, so chlorine has a -1 charge because it's picked up that extra electron. It now has more electrons than protons. Okay, now, does this whole compound, though, still have a charge of 0? That means, is there still, in total, when these things are joined together, the same number of protons as there are electrons? Yeah. Okay, they've traded them, but when they're joined together, it still ends up being neutral because all the protons and all the electrons are actually still there. All right. However, ionic compounds tend to break apart very easily. An ionic bond is not nearly as strong as the kind of bond that holds a molecular compound together. Okay, ionic bonds are fickle, let's say. Okay. Metals and non-metals, any element, is always trying to have what we call a full outer shell. Okay, electrons, if you look at Bohr's model, remember we talked about Bohr's model yesterday? Okay, if we have a sodium atom, okay, if we look on our periodic table, it tells us that sodium has 11 protons. Okay, so in its nucleus it has 11 protons. That means normally it also has 11 electrons. And electrons, according to Bohr, arrange themselves like this. And there's some truth to that. I mean, we know the electron cloud model is more accurate, but for simplicity's sake, we often show Bohr's model. Okay, so that's 10 electrons. Okay, in Bohr's model, okay, sodium would have 1 electron in its outer shell. Is that anywhere close to full? No, because that outer shell can hold 8 electrons, and there's only 1 in it. Okay, if you want to have a full outer shell of electrons in your sodium, which is easier? Find 7 or lose 1? Lose 1, okay? And most metals are like that. They tend to have outer shells that are less than half full, all right? And so they typically lose electrons, whereas, okay, chlorine, okay, as an example, okay, Chlorine is a nonmetal. Okay, it's got 2 in its first shell. Okay, 8 in the second shell. Okay, and then it has 7 in its outer shell, which is easier. Find a place to get rid of 7 or pick up 1. This is why sodium and chlorine get along so well. Okay, everyone follow? They have what each other needs. All right, now we don't want to take that too far, because then it means that once they have what they want, they don't have to stay together either. Okay, but that's actually sort of true of ionic compounds. The bonds are very weak, which is why ionic compounds typically dissolve easily in water. Does salt dissolve easily in water? Yeah, most ionic compounds do. All right, and the reason they do that is because the atoms now have what they need, and they don't have to stay together. So they just split, and you have these charged particles floating around in the solution. All right, and that's why those solutions will conduct electricity. Okay, now you've all been in the pool, right? When a lightning storm comes along, okay, and they always tell you what? Get out of the pool, right? Because you don't want to be in the pool if lightning strikes, because water conducts electricity, right? Okay, partially true. Pool water conducts electricity. Tap water conducts electricity. Distilled water doesn't. Pure distilled water is a molecular compound and doesn't conduct electricity. Okay? Has a conductivity of practically 0. Right? Whereas pool water is highly conductive, because what's it got in it? Chlorine and other particles, okay, other ionic compounds that are dissolved in there that help keep bacteria and mold and fungus from growing in the pool. All right, and so that's what makes a pool water highly conductive. Okay, and that's why you have to get out. If you could sit in a pool of distilled water, you'd be perfectly safe, but you'd be swimming in slime, probably, because stuff will grow in there, right? Okay. Okay, so when we're naming these compounds, like I said, this is hopefully a review for you. Okay, we always name the metal first, okay, and the non-metal second. So the name of the metal is stated in full. We don't change the name of the metal. Okay, sodium stays as sodium, magnesium stays as magnesium, etc. Okay, the non-metal, we change the ending to "ide." All right, so if it was "ene" or "eum" or whatever, it gets turned into "ide." All right, now there's a few elements in there that get a little bit tricky. All right, like sulfur becomes sulfide. Selenium can be either selenide or selenamide. Okay, really, I'm not going to care spelling wise. Okay, if you ended in "ide" and it's pretty close, I'm good with that. Okay, because there are a few of them that are kind of tricky, like tellurium and selenium are the same. They're selenide or telluride or selenamide or yeah, no, it's just telluride. There's some weird ones. Phosphorus, phosphide, okay, things like that. Everybody with me there? Okay, so we always change the non-metals ending to "ide." All right, so we have magnesium oxide, sodium fluoride, aluminum sulfide. Okay, now this stuff here, obviously we know what this is called. What is this? What's its name? Okay, we don't want to use a common name. What's its official name? Sodium chloride. Right, this is table salt. Okay, sodium chloride. Okay, what about this stuff? Magnesium chloride. Does it matter that there's a 2 on the end of it? It does not. Okay, we never indicate the number of atoms in the compound in an ionic compound, because there's only one way magnesium and chlorine can go together. All right, we'll talk about why that is here in a minute. Okay, but there's only one way that these two things can go together, and it has to do with how many people have heard of the swap and drop, or drop and swap, whichever way your teacher said it. Okay, that's the reason why there's only one way these two can go together. It's also why we don't need to say dichloride. Everyone will know that when magnesium is with chlorine, there's going to be 2. Okay. All right. So we have to remember to name both ions. Really important that we don't forget either one of them or name them out of order. Okay? I often see that people name the non-metal first for some reason. Okay, they just forget. Metal first, non-metal second. Easy way to remember that? Metals come first on the periodic table. Start on the left, move to the right, just like you do in anything else. All right? Names are never capitalized. That is the habit everyone has to break. Okay? the name of a chemical compound is not a proper name like Jane Doe, okay? It is a designation. Thus, it is not capitalized. All right, so a bit of a habit to break. I often see it. Okay, first couple of quizzes, I kind of, I'm a little lenient, but after that, if I see capital letters, you don't get it right anymore. Okay, because they cannot be capitalized unless you are starting a sentence with magnesium chloride. Then, of course, you would capitalize it. Okay, but if you're just writing it out, as a name, it is not capitalized. All right, so a true compound should have a net charge of 0. We talked about that before, right, with the trading of electrons. So if I have aluminum and chlorine, okay, they go together because they go together in this way: Al and 3 chlorines. Why is that? Because chlorines have a -1 charge and aluminum has a +3 charge. Okay, and I'll get you guys some periodic tables here shortly. Okay. That means if I'm going to have a charge of 0, I'm going to need how many chlorines to balance off this 3? Each chlorine has a charge of -1, and I need to get rid of 3 positive charges. I need 3, right? Because 3 times -1 is 3, right? Okay, so that's why they go together, and that's why you do that swap and drop thing, right? Al 3 plus Cl -1, and then you go, okay, so I take the 3 and I go here, and I take the 1 and I go here, and then I'm done. You guys recall that? Okay, we'll talk a little bit about that later, but okay, that's how we make sure our compound has a charge of 0, because now 3 times -1 is -3, and 1 times +3 is +3, 3 plus -3 is 0. All right, everyone okay with that? Okay, and again, you notice even though there's a 3 here, there's no indication of it in the name, right? Because there's only, again, one way that aluminum and chlorine can go together. Okay, now, here's something that's probably new to you. In the periodic table, okay, there are some metals that we call the transition metals, and they tend to be in the middle, where metals are transitioning to nonmetals, right? For some reason, these transition metals, in some situations, lose, let's say, 2 electrons, and in some situations will give away 3 electrons. Okay? Now, you may think, okay, so what? I still can name it iron chloride or whatever it happens to be. Okay? But here's the problem. Iron is one of these transition metals. It can be a +2, or it can lose 3 electrons and be a +3. Okay, everybody with me so far? Okay, so iron is one of the ones that can do that. Now, if iron has a 2+ charge and it goes with oxygen, it'll be FeO, right? Because the 2's will cancel each other out on the swap and drop. Does that ring a bell? Okay, we'll just show you that here real quick. So if Fe is 2+ and O is -2, okay, when we drop and swap, we get 2 and 2, and then we can reduce that to FeO. Everybody okay with that? Okay, now that stuff would be called iron oxide, right? Iron oxide. Everybody with me? Okay, what if instead iron with the 3+ charge reacts with oxygen, okay, which is -2? Well, now when I swap and drop, I get this. Okay, are those the same? They are not. But they would have the same name, wouldn't they? Well, that can't be right. If they're not the same compound, they don't have the same properties, I can't give them the same name. Here's what could happen. I'm doing my PhD on iron oxide, and I'm writing my big paper about all these experiments I've done with iron oxide, and I've mixed it with this and that and whatever else. And then someone reads it and decides, well, I'm going to replicate those. Okay? I'm going to do all that stuff with iron oxide that Mr. Quader did. Well, Mr. Quader was using this stuff. And he goes and uses this stuff and blows himself up. Okay? Because this is rust and this isn't. Okay? Is that a problem? It is. They can't have the same name. They're not the same stuff. All right? So we have to have a way to tell them apart. Okay? And what we use is Roman numerals. Okay? So on this one here, where I have the 2 plus iron, okay, I indicate that I used the 2 plus iron by putting a little Roman numeral 2 beside it. Okay? That way in the name, people will know it was the 2 plus iron. Because in the name, there's no way for them to tell. Okay? When they look at the formula, and when they look at this, they know it was the iron with the 2 plus charge. It had to be. When they look at this, okay, they know from the swap and drop that this had to be the 3 plus iron. The formula makes it easy, but the name doesn't. The name isn't clear. Okay? So when we're writing out the names of metals that have more than one possible charge, okay, we have to use Roman numerals. All right? Everybody good with that? Okay. All right. So how can you tell if something is a metal that has more than one possible charge? Okay? Well, on your periodic table, which looks just like this one, okay, you can see that in the top right-hand corner of every box are these little charge numbers. Okay? If the box has 2 numbers in it, that thing has more than one possible charge, and those are the 2 possible charges. Okay? We were just dealing with iron, okay? And you can see here that iron can be 3 plus, or it can be 2 plus. Okay? And they are listed from left to right in the order of most common. So the one on the left is most common, the one on the right is least common. Okay? Everybody with me there? Right? So you can see the transition metals are all in the middle here. Right? Are all in the middle of the periodic table. So if you're ever making an ionic compound that has one of those, okay, you know you'll have to figure out which one is in that particular compound from either the Roman numeral, or you'll have to figure out what Roman numeral goes in there. Okay, you'll also see that all the other ones have their charges listed here as well. Okay, so all of the non-metals have theirs. It's a little bit bigger and a little bit lower because I actually had to put it in myself and I just couldn't get it in the right place. Okay, and then the metals all have them in the right places. Okay, up in the top right-hand corner. Okay, everybody with me there? All right, so that's what we did there. Okay, we figured out that this iron here must be the iron 2 plus. Now, okay, if we're just looking at that, how do I figure out that that iron is the 2 plus iron? How do I figure out that I need to use, okay, if I'm just looking, I don't have this part here. Okay, if I just see FeO, how am I going to figure out what charge that iron had on it? Right. Well, yeah, the only way for them to cancel each other is if iron is 2, because oxygen is always what charge? -2. Okay? If you look at the nonmetal, there's no nonmetal that has more than one possible charge. Okay? They only ever have one charge. It's either -3 or it's -2 or it's -1. They only have one. Okay? So, what I do is I look at the nonmetal. Okay? Oxygen is always -2. Then that means, okay, as it's Peter, right? Yeah. Okay. As Peter said there, that if this is going to have a net charge of 0, if it's going to cancel out, the only way for that to happen is if this iron is the iron that's +2. All right. The same thing goes with the other one we dealt with. Okay. If I look at this formula, I have to do the same thing. I got to figure out which charge does iron have on it. Okay. I know that oxygen is always -2. There are 3 oxygens in this compound. So how many negative charges do I have? 6. Okay, so I know that I have a total of 6 negatives. Well, I need to have 6 positives for this to work out, and I've got to get them from iron. If there are 2 irons, every iron has to have a charge of 3. Okay, so this is the +3. Now I've got +6. Okay, those add up to 0, and I'm good. Okay, everybody follow me on that? All right. Now, I often have a few people that go, well, Mr. Coderre, I can just reverse the swap and drop. No, you can't. It works about 2/3 of the time. Okay? Works about 2/3 of the time. Give you an example of a place where that is not going to work. If I reverse the swap and drop, you're going to think Mg has a charge of what here? Because that's a 1, right? When there's no number beside it, it's supposedly a 1. Well, that doesn't work. Okay? There's a few other situations where it also does not work. Okay, this way always works. Okay, if you reverse the swap and drop and just take those numbers up, it'll work 2/3 of the time. Okay, so if you're desperate, you can try it that way. It'll work 2 out of 3 times. Right? But I would say this way I just showed you, where you do the kind of multiplication, that way always works. All right, so other examples here. Okay, we got copper 2 sulfate. Okay, that's another example. Okay, there's just anytime you have the multivalent metals, we call them, or the metals with more than one charge, then you have to use the Roman numeral in their name. All right. Okay, I want you to try, let's say, the first 4 here. Okay, and then we'll go over them together. None of these ones are multivalent. You're not going to need Roman numerals in any of these names. Okay, these are just regular ionic compounds. I want you to write the names of just the first 4 for now. Okay, and then we'll go through them. I'll give you 2 minutes here to get that done. Okay, so I'll do the first 4, and then I'll call on other people to do the other ones as we go through here. Okay, so our first one, NaCl. Obviously, that's pretty easy because we already did that one. Okay, so we have sodium chloride. Okay, because this stuff's sodium, that stuff's chlorine. I changed the ending to "ide." Okay, again, no capital letters, okay, on any of those. All right, our second one, K stands for what? Potassium, and F stands for fluorine. All right, so this stuff is potassium fluoride. Okay, and fluoride can be spelled many different ways. Okay, sometimes it's spelled OU, sometimes it's spelled UO, sometimes it's just spelled with an O. I don't care. I know what it is, no matter how you spell it. Okay, so potassium fluoride, that'll work. Okay, number 3, H stands for hydrogen, I stands for iodine. So this is hydrogen iodide. Okay, and then our last one here for number 4, we've got Ca, which stands for calcium, Br, which stands for bromine. This is calcium bromide. Hydrogen, when listed first in a compound, is a metal. Okay, I know it's a gas, and that's often tricky to people, but hydrogen is actually the most metallic element there is. It just happens that its boiling point is very, very low. Okay, when you actually if you could get hydrogen to be a solid, which it has to be really, really cold, it looks just like a metal. Okay, it also behaves in a very metallic fashion. Right, because it only has 1 proton and 1 electron, it can very easily lose its electron. Right, and behave like a metal. It can also sometimes behave as a nonmetal, okay, if it is listed in a compound second, okay, like for example, like this. Okay, in that case, hydrogen is acting as a nonmetal. Right, that's methane. That's what's in farts. Okay. Yeah. In H2O, hydrogen is first, but in actual fact, water can also be written like this. HOH, right? Water, if there's a rule, water's the exception to the rule. Okay? And so, yeah, it's weird. Water is the most important thing we have, and it's the exception to every rule we make, it seems, in chemistry anyway. All right? But you're right. We can kind of nitpick like that, but in general, hydrogen is listed first. It's a metal. Okay, it behaves as a metal. All right, let's have you guys do up to number 10. Okay, and then we'll go through those, and then we'll do the last 4 after that. All right, so let's give these ones a try. Let's have Emma Thorne tell me what number 5 is. Aluminum acetate, right? Okay, and we'll still say aluminum like North Americans do, because the International Union for Physics and Applied Chemistry changed it, and they say it should now be aluminium. I don't like that. I'm supposed to call it aluminum, because that's the way we call it here. All right, let's have Sadie. Can you tell me number 6? Cesium sulfide. Good. Okay, Michael, tell me number 7. Sodium oxide. Okay, and Everett, you can tell me number 8. Barium selenide, okay. Okay, that could be selenide like this, or we could also write it as selenimide. Okay, either one is fine. Okay, 9, let's have Aiden tell me number 9. Radium telluride, good. Okay, and number 10, let's have Lucas. Tell me that one. Lithium fluoride. Okay, looks like we're getting it there. Now, I want you to look at your sheet and see how many times you capitalized those names. Okay? And then feel shame for every time you did it and try not to do it on the last 4. Okay, so I'll give you a couple minutes on the last 4 here. Okay, let's have Stephen tell me what number 11 is. Rubidium sulfide, good. Okay, and Samuel, how about number 12? Strontium iodide, right? Okay, and Alex. Calcium oxide, good. Okay, and Emma. Magnesium selenide, right? All right, looks like you guys are getting it. What do you suppose Tuesday's quiz will be on? Yes, okay, it'll be on naming, okay? Okay, now these ones have some of those multivalent metals in them where you'll need the Roman numeral. Okay, so what we're going to do is we'll go through, obviously we've done number 1 already, we'll go through it again, and we'll go through 2 and 3 together, and then you guys can try the rest of them. Alright, so I want to name this thing here, and we said if I'm going to figure out what Roman numeral goes on this, because I know it's iron something oxide, okay, because it's an ionic compound, I still got to follow those rules. What I got to figure out is what Roman numeral goes there. Okay, and we said the most reliable way to do that is to go, all right, oxygen is always -2. We always look at the non-metal because they never have more than one possible charge. Okay, every oxygen's -2 and there are 3 of them. That gives me a total of 6 negatives. That means I need to have 6 positives. Well, 6 divided by 2 is 3. Okay, that means this is iron 1, 2, 3 oxide. Okay, and then we have cobalt something sulfide. Okay, again, this is where that reversal of the swap and drop doesn't always work because right now they're both 1s. Okay, so that's not going to work. But if I do what I did over here and look at the non-metal, sulfur's charge is always -2. If it's -2, cobalt has to be +2. So this is cobalt 2. Okay, sulfide. And guys, you're not going to need your Roman numerals past, I think, 4. Okay, so it's I, IV. Okay, that's 4. Past that, I don't think you're going to need to know your Roman numerals. Okay. All right, and then for number 3, we've got manganese and chlorine. So this is going to be manganese something chloride. Okay, chlorine is always a -1, and there are 4. Okay, that means that the manganese has to have a charge of 4, +4, right? But okay, so we'll go IV. Okay, manganese 4 chloride. give you guys some time to try the others there, and then we'll go through them together here in a few minutes. Okay, so let's give these ones a try here. Okay, let's have... Let's have Sierra tell me what number 4 is. Copper... Which Roman numeral? 2, right. Copper 2 sulfide. Okay. And number 5. Let's have Danielle tell me that one. Okay. Tin 2 telluride, right? Tin's not tin 2. It's going to have to be tin 4. Okay. Telluride's -2, right? Okay. If every telluride is -2 and there are 2 of them, then we have 4 negatives. Okay. That means this tin has to be a +4. So we're looking at tin IV. Okay. Telluride. So there's another one of those tricky ones where that reversing the swap and drop doesn't work. Okay, if we reverse the swap on drop on that one, then we don't get it right. Okay, so there's the 1 out of 3. Okay, that it doesn't work for. All right, number 6. Let's have Aiden. Can give me that one. Mercury 2. Oh. Yes, that's right. Mercury 2 acetatide. Okay, let's go with Nick this time on number 7. Right, polonium 4 iodide. Okay, let's have Carson tell me number 8. Yes. Yep. No, not 2. It'll have to be... Okay, because we've got 6 negatives here. Okay. This antimony has to be 3. All right. Sulfide. Okay. Number 9. Let's have Peter give me that one. Nickel 2 nitride, yes. Okay, and number 10. Let's have Sadie give me that one. Didn't get 10? Who's got 10 done? Okay. Right, yes, ruthenium 4 oxide. All right, good. Looks like we're getting it there, guys. Okay, it just takes a little bit of practice, but they're not terribly difficult. All right, hopefully we'll get kind of into molecular here today, and then we'll continue it actually on Monday, because tomorrow we're going to be showing you how to use the Google Classroom stuff. Okay, so we'll talk about molecular here. We might get to practice a couple before the bell goes. Okay, so molecular compounds arise when, okay, 2 nonmetals, okay, bond with each other chemically, okay, to form a new substance. Here's the thing about nonmetals. They can't be trading charges because they're all negative. Okay? They can't all lose electrons. Someone has to pick them up. Okay? So a molecular bond is a lot different than an ionic bond is. Okay? In fact, molecular bonds are often called covalent bonds. Okay? The reason they're called that is because the shells of an electron, or sorry, the shells of an atom, okay, the electron shells, are often called valences. Okay? Now, the outer shell is where the valence electrons, okay, the ones that get involved in chemical reactions, are located. Okay? And so, in a molecular bond or in a covalent bond, the electrons get shared. Remember, we said that atoms want to have their outer shell full. Well, if they're both nonmetals, there's no way that they can both have that. Okay, they can't trade electrons and both have a full outer shell. It doesn't work. Right? So what they do is they share them. Right? So an example is water. Okay, water is a molecular compound. So when we look at this one, again, it's one exception that proves the rule because hydrogen was listed first. Okay, but yeah, remember that from before. Okay, what happens here is hydrogen normally has one electron in its outer shell. So we'll just say that this electron here is hydrogen's. Okay, and this blue one here is oxygen's. Okay, and the same thing down below here. Right? We'll say that this green one here is the one that belongs to this hydrogen, right? And this blue one is the one that belongs to oxygen. So all the other ones belong to oxygen. Now, the first shell of an atom can hold 2 electrons. Is hydrogen happy? Yeah, it's kind of got 2 electrons in its outer shell. All right? And same up here. Okay? This hydrogen is reasonably happy. It kind of has 2 in its outer shell because it's sharing one of oxygen's. And by the same token, oxygen is also happy because its outer shell has 8 electrons in it, even though 2 of them aren't technically its. Okay? 2 of them technically belong to the hydrogen. But because they're sharing them, everybody's pretty happy. But that also means they have to stay together. Because if they separate, then they don't have outer shells and they're not happy and complete anymore. Okay, so in order to be complete and fulfilled in life, apparently, okay, this is what atoms have to do. All right, so this is a much stronger, more stable bond than an ionic compound would have. All right, so typically, molecular compounds have different behaviors. Okay, they don't typically dissolve as easily in water as ionic compounds do. Some do, but not all. Okay, and none of them will have solutions that conduct electricity. Okay? So if you put sugar into distilled water and got it to dissolve, it would not conduct electricity. Okay? Because sugar is a molecular compound. It doesn't break up into the positive and negative parts like salt does. Right? So the solution would be non-conductive. All right? So those kind of bonds lead to different types of physical properties, and that's something else that we'll talk about next week as well. Okay, so the big thing here, okay, molecular compounds happen when 2 nonmetals react, okay, and no one gets to keep the electrons. The electrons are shared, okay, between the 2 elements in a covalent bond. That's kind of the big key points there for what's a molecular compound or how's a molecular compound different, okay, from an ionic compound. Okay, questions on that? Okay, naming molecular compounds. Molecular compounds are the ones that have all the prefixes. Okay, because there's no way for us to know how many of something would go with something else. It can be any number. Okay, because they're sharing the electrons, it's quite unpredictable. Right? So when I'm naming these, okay, if I've got carbon and sulfur together, okay, it's carbon disulfide. I have to tell people there's 2. There's a possibility there could have been more. Okay, I have to tell people how many carbon there are, how many sulfide there are. In fact, this isn't named correct, or this one is named correctly. Sorry. Okay, dinitrogen, and this one is not named correctly. What should go in front of oxide here? Mono. This should be dinitrogen. Okay, monoxide. All right, we have to put these prefixes in order to name the compounds correctly. All right, so we write the name in the order the formula goes in. So if carbon's first in the formula, carbon goes first in the name. Okay? We don't change the ending of the first nonmetal. Okay? We leave it as it is. We only put the "-ide on the second one. All right? So kind of with all compounds, whatever finishes the compound ends in "-ide. Okay? All right. Now, prefixes. We probably got to know those, so we'll write them all down. Okay? 1 is mono, 2 is di, 3 is tri. It's pretty much like your shapes. Okay, 4 tetra, okay, tetrahedron. Okay, 5 penta, and so on. Okay, we'll pick that up on Monday. Please, if you can, look up your username and password for tomorrow. If you come without it, I can probably look it up, but it'll be a lot faster if you know it when you come. Okay.